Hello, and thank you for your interest in my poster presentation. Today I'm going to be talking about device-independent Oblivious Transfer from the bounded quantum storage model and with computational assumptions. This is joint work with Broadbent, and yeah, let's get into it. So we'll start by talking about what is Oblivious Transfer. It's basically this cryptographic primitive where there's a sender and a receiver. The sender is going to input 2 bits, and the receiver is going to select and receive only one of those 2 bits. In terms of security, we have security for the receiver and security for the sender. Security for the receiver means that the sender should be unable to learn which bit the receiver chose. And when we talk about security for the sender, the receiver should be unable to learn both bits. So they should only be able to learn one of the 2 bits. Now this is pretty simple, but despite this simplicity, unconditionally secure Oblivious Transfer is actually impossible, even with the assistance of quantum communication. So what this means is that if we want some sort of secure Oblivious Transfer, we're going to need some sort of additional assumption. So the additional assumption that we're going with is the bounded quantum storage model. So what this means is that we're going to assume that the receiver's quantum storage is bounded during the execution of the protocol. Intuitively, what this means is that if I'm the sender and I send more qubits than the receiver's quantum storage can handle, then it's going to force the receiver to perform some sort of measurement which will effectively limit their ability to cheat. And under this bounded quantum storage model, you can actually get an everlastingly secure Oblivious Transfers protocol. So the receiver's quantum storage could become unbounded after the protocol, but that doesn't really matter for security. And now look at this protocol here without the device independence. This protocol is actually going to be very similar to the protocol found in this second reference here. The difference is that in this reference, they're using conjugate coding, or sometimes known as BB84 states. In our case, we're going to be explicitly using the 4 bell pairs. The reason for that is for compatibility with the device-independent component of this later on. Here, we don't really need to worry about this. This is mostly for the sake of notation. Like these V alpha and V beta, these are just bits that together denote which of the 4 bell pairs that we're dealing with. But here's the protocol. So there's a device that we trust. It's going to be producing bell pairs, one of the 4 bell pairs at random. It's going to send the first qubit to the sender and the second qubit to the receiver, along with these bits V alpha and V beta. The sender is going to measure in a random basis. So this could be the computational basis or the Hadamard basis. The receiver, they're always going to measure in one basis. And it's going to be according to their choice bit. So if I'm the receiver and I said, I wanted C is equal to 0 for the Oblivious Transfer scheme. And if I chose C is equal to 0, I'm always going to measure in the computational basis. And if I chose C is equal to 1, I'm always going to measure in the Hadamard basis. And by basically always measuring in one basis, it guarantees that I'm going to get one of the 2 strings. So we're going to repeat this procedure n times, and then once this is all done, I'm the sender, and I'm going to randomly pick 2 hash functions. And then without worrying too much about these W alphas and W betas, I'm going to apply the F0 hash function to all rounds where I measured in the computational basis, and I'll apply the F1 hash function to all the rounds where I measured in the Hadamard basis. Then I'll actually publish these hash functions along with the measurement basis that I chose for each round. And this means that the receiver is now able to select the rounds where their measurement basis coincided with the sender's, and then they can apply the appropriate hash function, which guarantees that they get at least one of the 2 strings. And we can see pretty easily how this breaks down if we had not made the bounded quantum storage assumption. So right at this step here, if I'm the receiver and my quantum storage is unbounded, then I could just ignore this step and store my qubits and not measure according to my choice bit, and just wait until the sender eventually publishes their measurement bases, and then I can copy everything that the sender did, measuring in the same basis, and then this would enable me to get both strings. So the bounded quantum storage assumption is quite crucial here. And the key thing that we're interested in is the fact that we had to trust the fact that the device was accurately creating these bell pairs. Also that our measurements were being done correctly. So this leads us into the device independent component. So what is device independence? It's basically treating the device that we're dealing with as a black box. So we don't trust that the device is functioning accurately. There could be something wrong with the device. It could be, some malfunctioning, or the device could have actually been created by someone with malicious intent. So we don't trust it. And what we can do, though, is we can use classical interaction with the device to test the device's behavior. So these are usually under the name of self-testing protocols. The way this is usually done is using Bell inequality violation. So we use the classical correlations to see if they violate a Bell inequality, and if so, we can say, hey, there's something quantum going on inside the device. The problem is that Bell inequality violations come with loopholes that have to be closed in order for the conclusions to be valid. And one problematic loophole is this locality loophole. It basically requires that the device components can't communicate. And this can be practically hard to enforce. It means that we would have to perfectly shield each component of the device between rounds, well, I guess during rounds, and it also means that if we didn't use perfect shielding, then we would have to separate the components of the device by a sufficiently large distance such that the time it takes to complete the protocol would be faster than information to travel from one component to the other. So instead, we can take a slightly different approach, or a very different approach, and use a computational assumption. And the computational assumption is that the device can't break the computational assumption during the execution of the protocol. It can break it after, but during the execution, it's assumed that the device can't break it. And the problem that we're dealing with is the learning with errors problem. So if we assume the device can't solve the learning with errors problem during the execution of the protocol, then we're going to be able to say that something's quantum is going on inside the device. Specifically, a lot of this self-testing protocol, which is coming from this reference here, reference number 7, which is, and also it's used in reference number 6 here. This self-testing protocol relies a lot on these extended noisy trapdoor claw-free function families, along with the properties. And basically, the learning with errors problem can be used to construct this family. And so without going into the details of this self-testing protocol, the main thing that comes out of it is that if we have this computationally bounded device, it's passing the checks of this self-testing protocol, then we can say that the device has not only prepared a Bell state, but it's also measured it according to the measurement bases questions that we've supplied it. So maybe a little bit of a peek behind the curtain of what's going on with this self-testing protocol is that there's basically 2 types of rounds that can occur. Some rounds the device will create a product round, some rounds the device will create a product state, and other rounds the device will create a Bell state. And the type of round that we're dealing with is going to be determined by two keys, but the device is never going to be given trapdoors, and basically by properties of this extended noisy trapdoor claw-free function family, the device is never going to be able to determine, am I in a product round, am I in a Bell round, so it won't know whether it creates a Bell state or a product state. But the testers, Alice and Bob in this case, they would be able to determine what type of round the device is in, and it would also be able to, they would also be able to determine precisely what state is created. And so they can use this to check if the device is functioning as intended, and if so, then they gain some confidence about it. And so we need to modify this slightly for the setting of Oblivious Transfer, because in this setting of Oblivious Transfer, the sender and receiver don't trust each other, so they can't cooperate necessarily to test the device. So instead, we're going to have Alice, who's eventually going to play the role as the sender. Alice will be the sole verifier, and then Bob will essentially act as a relay between Alice and the component of the device held by Bob. So now that we have this self-testing / device independence, and we have a Oblivious Transfer protocol in the bounded quantum storage model, we can combine them both to get what we want. So in summary, we're going to execute n rounds of this modified self-testing protocol where Alice / sender is the sole verifier. But since Alice is then going to be generating all the input, the receiver can't use all the input generated by the sender. So for some rounds, the receiver is going to do their own thing, aka measure according to their own basis that's determined by their choice bit. And they'll mark these rounds and let them belong to a set I. And then when it comes to testing the device, the sender is going to test all the product rounds and some subset of the bell rounds. So this means that the receiver / Bob would have to send over his output that he got for these rounds, but he will explicitly exclude information from the rounds I, because in those rounds, that's where the receiver has done their own thing, measured according to their own choice bit. And then once that's done, assuming that the device has passed the self-testing, the checks of the self-testing protocol, and not aborted, then we can identify what rounds are usable, which are going to be all the rounds where bell states were created and the rounds where the receiver measured according to their own choice bit. And then the rest of the protocol is essentially the same as over here. And yeah, that's pretty much everything. And thank you for listening.